Hi everyone, my name is Chang Liu. I'm a second-year graduate student at Northwestern. And today I'm very happy to talk about a very interesting peculiar type 1a supernova 2020 JGB, which we believe is triggered by the double detonation of a thick helium shell. Type 1a supernova are known to come from thermonuclear explosions of white dwarfs, but still it remains highly uncertain what really ignites the white dwarfs. Traditionally, people believe that a white dwarf can accrete from its companion and reach the Chandrasekhar mass limit and explode. These scenarios can reproduce the observational properties of a type 1a supernova, but it cannot reproduce the required number of type 1a supernova we observe today, which means other scenarios are also needed, such as the double white dwarf merger scenario, or in this case, the double detonation scenario, in which a detonation of a helium shell triggers the detonation of the white dwarf itself. These scenarios is tested to be successful in supercomputers, but we still need some smoking gun evidence to confirm that such objects really exist in the universe. There are some properties that can distinguish double detonation supernova with type 1a supernovae that arise from other scenarios. For example, if you go early enough into the explosion of double detonation white dwarfs, you would expect a very unusual red bump in the light curve, which has been reported in a few objects, but it is very difficult to detect. On the other hand, if the helium shell is more massive than we would expect for a normal type 1a supernova, then a significant amount of iron group elements will be synthesized in the shell, which would absorb the blue photons from the supernova, causing the transient to be subluminous as well as extremely red. On the other hand, there will be a significant amount of helium that is left unburned in the shell, which we would also expect to observe. For supernova 2020 JGB, it is highly likely that we have detected both properties for a thick helium shell double detonation event. First, we show the spectral sequence of 20 JGB, along with the spectral sequence of the prototype thick helium shell double detonation event, known as 18BYG. These two spectral sequences are pretty similar, especially if we look at the spectrum near the peak. Basically, there are no flux at all in the blue region, which is very unusual for normal type 1a supernova, but we would just expect them in double detonation events because we would expect a large amount of iron group elements that are absorbing the blue photons. We also compare the light curves and the spectra of 20 JGB with some double detonation models, and we see that the majority of the spectral properties, the absorption features, the continuum, can be very decently fit by some models with a pretty thick helium shell, as massive as 0.13 solar mass. Indeed, it is a little bit challenging to model the spectrum in G-band because there are some non-local thermal equilibrium effects, which are not included in our models. But we're still very confident to say that 20 JGB is fairly consistent with a sub-Chandrasekhar mass white dwarf ignited by a massive helium shell. Another very interesting fact is that we detect a very prominent absorption feature at 1 micron, which is never seen in normal type 1a supernova. There can be some possible origin for this 1 micron feature, including the most natural gas, the helium, because we would just expect unburned helium in this event. Indeed, there are some other possibilities, but for all the other elements, if they were the case, then some stronger lines would also be expected to be observed. But we just did not detect them in all our spectra, meaning that the other elements are just not that likely. Another very supported evidence for the helium-1 scenario is that if we plot the expansion velocity of the 1 micron feature with respect to the rest wavelengths of the helium, then we can see that the expansion velocity is fairly consistent with that of the high velocity feature of the calcium-2 infrared triplet, which in a double detonation scenario is believed to also originate in the helium shell. So we'll just expect them to have the similar velocity, and we see it. Unfortunately, we did not detect other helium lines either. Other lines are much weaker than the 1 micron line, but since we just did not detect them, we're not 100% sure that we really see helium in the spectrum of 20 JGB. Interestingly, the 1 micron feature is, although the 1 micron feature is very unusual in normal supernovae 1A, in all the double detonations events with near-infrared spectra available, we see this 1 micron feature. And again, the expansion velocity of the 1 micron feature, assuming it is associated with helium, is very comparable with the high velocity feature of calcium-2 infrared triplet, although the velocity itself varies strongly from events to events. Another thing we did is we got a lovely spectrum for the host galaxies of 20 JGB, which clearly indicates it is a star-forming galaxy. And if we plot a specific star formation rate versus the stellar mass for the host galaxies of these double detonation events, we can clearly see that double detonation can happen in either star-forming or passive galaxies, which is a strong hint of the progenitor systems of these subtype of type 1A supernova. Although we do need a larger sample in the future for more detailed studies of their progenitor systems. That is the whole story of these objects. We do need some future observation for a larger sample of these events to have a better understanding of type 1A supernova and helium shell double detonation.